Okay, this is part 2 of 2 in our lecture covering chapter 8 from your book on experimental research or true experiment design. So we were talking previously in the first part about independent variables and the idea of the null effect, where there's no connection between the manipulation of the independent variable and the dependent variable, meaning there's no cause and effect relationship. Let's talk a little bit about how we go about designing and manipulating our independent variables. So let's talk about how we go about manipulating our independent variables. The first type that I want to talk about, first type of manipulation, is a simple and direct one. And the Stroop experiment that we discussed in the first part is a really good example of such. So this is really an independent variable that is manipulated in terms of which condition you're receiving, right? The congruent condition or the incongruent condition. Now, in this case, each person receives both levels of the independent variable. We'll talk about what that means in terms of design in a moment, but the manipulation is very simple and direct. So if you remember, there's the congruent condition where the color red, for example, is printed in a red font, but in the incongruent condition in list number 2, the same color red is printed in a green font, for example. So the independent variable being manipulated in the Stroop study is the word type, congruent or incongruent. Therefore, you have your two levels or two conditions. Each independent variable must have at least 2 levels. In the Stroop example, there are 2 levels. It really looks to quantify the impact of the independent variable word type on our dependent variable, which is response time. So the difference in the average response times of list 1 to list number 2 is the effect of processing of inhibitory control cognitively, which is created by the different levels. So when we manipulate an independent variable, we want to look at effect size, we want to look at reliability. These are all things we want to examine. Now, in the case of the Stroop test, it has very strong reliability. So generally speaking, the incongruent list response takes about twice as long as the congruent list. And this is an extremely robust and reliable finding. Many people have taken the Stroop test and incorporated it into their own various studies of different types. I myself did an experiment when I was an undergraduate that involved, these days would never be approved by an IRB, that involved giving differing quantities based upon body weight of vodka to some of my friends who were, of course, an example of what they call a convenient sample, and then administering the Stroop test prior to and then after consuming alcohol. Right? I was interested in substance abuse research. I still to this day can't believe that ethically I was allowed to do that as an undergraduate with no institutional review board, but that was the bad old days. Ultimately, though, the Stroop test has been incorporated into lots of different studies, and that effect, that fact that the incongruence versus congruence condition produces a longer amount of time to read the incongruent list is extremely robust, and it's very reliable, and it's been found in lots and lots of studies. So it has good reliability, this measure and this manipulation of the independent variable. There's some really interesting findings. People have done variations and replications of the Stroop test. They've modified it to incorporate other aspects. There's theories that emotionally charged material requires increased inhibitory control, that meaning that if you're emotionally invested in something, it's even harder to inhibit your sort of automatic prepotent responses. And so they've done things like looking at emotionally charged versus neutral words. What they found is that if I give you a Stroop list of words and I say read the color of the font, and the list includes negative emotional words such as war, kill, cancer, and then I give you another list that has a neutral word list like clock, chair, or windy, it takes you longer to complete the list with the negative emotionally charged words than the sort of benign words. So this effect has been shown to be reliable across different aspects of cognitive functioning even. So that's an example of a very simple and direct manipulation. You present the person in sequence either the congruent or the incongruent list. That's very obvious what's going on even to the participant. Usually they understand what the test is doing. As opposed to that, we can engage in more covert or indirect manipulations. So as we've mentioned, a good theory generates a testable hypothesis. We derive hypotheses from theories, and it's often framed as an if-then or a predictive statement. And remember that these hypotheses are for a good scientific approach, for a good scientific rigor, are formed a priori, prior to the gathering of the data. Okay, so that's that Latin term that means, as opposed to a posteriori, which means after the fact, or post hoc. You've also heard that, I'm sure, after the fact. A priori is when you make your predictions, when you form your hypotheses and present them prior to looking or collecting any data. There's a really good example of an indirect manipulation, a covert manipulation in your book, and this is called the facial feedback hypothesis. And this essentially is based on the research of Strock, Martin, and Stepper from 1988. And it states that facial movements themselves can reenact particular emotional feelings. It's kind of this old annoying adage, that if you go around with a smile, that maybe you'll feel better and be happier. But the essential idea is that these researchers figured out this intuitive and interesting way to induce the facial expression in the person without telling them what it is they wanted them to do. Okay, so the point is, if I simply say, I want you to make a happy face, I want you to make a sad face, what you're doing is you are sort of, there's a bias that's introduced. The individual has probably a strong tendency to want to assist the researcher, that you're essentially giving away what it is, and that it ruins the effect of being able to measure people's emotions in a natural setting. What they determined was, if you had someone take a pencil or a pen and you have them hold it in their teeth, like so, it induces a smile. By having to hold something in your teeth, you're moving up the sides of the mouth. You're essentially utilizing the same muscles in the face that induce a smile. If you have them hold their lips, you're inducing a frown, right? A more traditional sad face, so to speak. What you would do then is have the participants hold the pen in either their teeth or in their lips, which is indirectly, covertly influencing them to either smile or to frown, and then you present them with a series of comic strips, and you ask them to rate how funny these comic strips are. What's really strange about this study, which is really interesting about the way our faces can affect our emotions, is people who were holding the pencil or the pen in their teeth gave higher ratings of things being funny than if they were holding it in their lips and producing the frown. So there was also a control group that held the pen in their non-dominant hand and rated the same comic strip, meaning that you're still doing something to them. You're still showing them, oh, you're in this condition. You have a part in this study that involves this pen being in your hand, but it has nothing to do with your facial expression, and therefore that's the sort of no intervention control that's available to them. So what they found in this, it was the idea that holding it in your teeth caused you to find things more funny than if you held it in your lips and created the frown. So this indicates there was a difference in treatment groups, and by having that control group where they held the pen in the non-dominant hand, it's not. They were saying it's not confounded. This finding is not confounded by some unrecognized difference between covert smiling and covert frowning versus the pen hold. So in experimental design, we often end up with a need for large sample sizes for groupings to assess the true differences related to the independent variable of study. We've talked about this idea of a power analysis that tells you how big a sample you're going to need to find your hypothesized effect. So a characteristic that we have to be cognizant of, and which is why this manipulation factor, this covert manipulation, is sometimes better than sort of overt or simple manipulation, is what's called a demand characteristic. And I was referring to this in the previous slide about the idea of telling the person what it is you're measuring, what you'd like them to do. Participants form expectations as to the true purpose of a study, and then they alter their responses to the experiment in order to fit in with their perceived or preconceived notions of what the study is about. So a demand characteristic is essentially people's general desire to be helpful or to confirm what it is that you're looking for. And this is essentially the placebo effect. And so we really want to try and design our studies in such a way that we diminish or minimize demand characteristics. We're not introducing bias into how people respond. We want them to respond, quote unquote, naturally, right? And a demand characteristic is an unnatural interjection into your study that can really mess with how people respond, because they have a preconceived notion of I should be doing this, or I shouldn't be doing this, or oh, they're trying to figure out this, so therefore I'm gonna behave differently. What you don't want is you don't want people second guessing the study. You don't want them sort of trying to figure out what it is you're measuring and therefore having that in their head and influencing or altering their behavior. You want to try and get them to behave the way they would generalizably out in the real world. Merzenich and colleagues tried to control for placebo-like effects in their brain training study by having that comparison group, that active control group, where they had them engage in computer use. Same schedule, 60 minutes a day, 5 days a week for 8 to 10 weeks. This is the same amount of time in front of a screen that the people in the experimental brain plasticity training treatment group had. And again, you want to then assess cognitive performance or group difference at the end. There is a study by Feroji and colleagues that countered the suggestion that improvement was itself a placebo. They basically came along and they said that the reason why people who underwent brain plasticity training in the Merzenich study did better in terms of their cognitive performance was because of a demand characteristic or a placebo effect. What they pointed out was that perhaps it was clear from the way the researchers designed the study what it was they were measuring. The people were told, you're participating in a brain plasticity training. You may end up in a condition that is meant to increase your brain plasticity, or you may end up in a control group, or you may be in the no contact, control group where all you do is you get measured once and then again after a certain period of time, after this 8 to 10 week period. So what they were arguing was it's not the brain plasticity training that caused people to do better on their measures of cognitive performance. It's the fact that they were told that they may be receiving a brain plasticity training which is theorized to improve your cognitive performance. The way that Feroji and colleagues tested this in the unfortunately abbreviated journal PNAS, which is oh gosh, now I'm going to forget what it is. But essentially, it's a reputable science journal. But the idea is that they tested this theory of the placebo effect by recruiting with 2 different types of flyers. They utilized suggestive and non-suggestive flyers. So in one flyer, participants were clearly told that you're being recruited for a study about brain plasticity. In another flyer, that was left out. That information was not presented. And what they found is that people who were recruited using a suggestive flyer performed better than those that were recruited using the non-suggestive flyer. They basically were able to demonstrate that the placebo effect was playing a role, that the demand characteristic was in fact perhaps was perhaps the real reason why people did better with brain plasticity training. This problem, this demand characteristic problem, is why we have the development of an even higher, more golden standard within experiments, which is the idea of the double-blind randomized controlled trial study. You'll hear this phrase or something very similar, randomized controlled, double-blind randomized controlled. A lot of times we think about this in the context of research on different types of medications or drugs or COVID vaccines, whatever it is. But it happens a lot as well within other types of intervention and treatment research within psychology, and we'll talk a little bit about that. But the idea is that a double-blind randomized control study is really the best way, the best antidote for reducing placebo effects. So in a double-blind study like this, what double-blind means is twofold, basically. The idea is that the first part of that blindness is that the person who is a participant does not know what condition they've been assigned to. So you obviously, you're not told, oh, you're going to the brain plasticity group, oh, you're going to the control, you're going to the no contact control. The second part of the double blind is that the researchers themselves who are doing the random assignment also do not know which group the people have been assigned to. When the researchers gather the outcome data, when they do the cognitive measures to test people's performance, they are also not told which condition that person was in. The concern is that even the researcher, by virtue of knowing what condition the person is in, may implicitly in subtle ways affect the way they gather data, the way they talk to the participant, the way they inform them of their condition. Essentially the idea is that, I'm sorry, not the way they inform the condition, the way they inform them of what their instructions are for the study. The problem is that perhaps even the researcher is influencing and introducing bias. So in a double-blind study, People are randomly assigned to a group, and the people that are gathering the outcome data, the dependent measure, dependent variable information, also don't know which group the person was assigned to. So these are the examples of the two different types of flyers that were used in the research we were just talking about. The one on the left is obviously an example of the sort of more overt and potentially, in this case, suggestive flyer. As you can see, it says brain training and cognitive enhancement. Numerous studies have shown working memory training can increase fluid intelligence, and then it has a scientific reference there to a couple of articles. Participate in a study today. If you notice, even the email address is gmubraintraining@gmail.com. So it's really very, very clear what's going on. The little tag that you pull off of the flyer says brain training on it and has the contact information. On the right, and this was done at George Mason University, so that's the GMU part. On the right, you see the non-suggestive flyer. It just says email today and participate in a study. Need Sona credits? Sign up and study today and earn up to 5 credits. Participate in a study. The email address has been changed to just the email address name associated with the researcher, and then even the little tags that you pull off of the flyer don't say anything about brain training. So this is just an example of how they manipulated the independent variable of suggestive versus non-suggestive flyers for recruitment. So staged manipulation is something that we sometimes engage in. This is how we manipulate an independent variable. If you think about the Milgram study, it's an example of a staged manipulation, but this is basically where you try to fashion the psychological state or the social situation that is the topic of investigation within the context of the study. So Milgram was interested in obedience to authority, so he created a situation in which obedience and authority were relevant. Another example from your book is Bushman and Baumeister in 1998. They did laboratory studies of interpersonal violence. They obviously didn't have people engage in real physical or aggressive behavior. What they did is they had participants receive positive or negative feedback on essays they were instructed to write as part of the study. They then participated in a game rigged. It was rigged for them to win, in which they competed against the person who rated their essay, right? So I hope you follow that. Essentially, they are instructed to write an essay. They receive positive or negative feedback from a rater on their written essay, and then they subsequently are participating in a game with the essay rater. Now, the game is rigged so that they always win, okay? After the game win, they are told that they get to blast their opponent with a loud noise like an air horn, and this person is, out of sight in the game room. No one's in the room at a level chosen by the person who had won. So essentially what's happening is you're allowed to blast the person you just beat because you won ostensibly. You get to choose how loud or how many decibels this blast is going to be while they're alone in another room. Now, of course, this is a Confederate and there's no actual blasting of anybody with any loud noise. So it has some similarities to the Milgram study in that sense too. The decibel level of the noise blast chosen by the participant is recorded, and in fact this is the dependent variable. This is the outcome measure. The findings were that only people with certain personality traits responded aggressively when faced with an opponent who they believed had insulted them or given them a negative review or negative feedback on their essay. What they found was that people that scored high on certain traits of narcissism, for example, being extremely egotistical, were the only ones who tended to escalate to give large amounts of decibels delivered to their supposed foe they defeated in this task. They interpreted this result to support the theory of what they call threatened egotism as one pathway for interpersonal violence in the real world, that people who were high on this particular personality characteristic, if they felt they had received negative feedback from someone in their life, that constituted a threat to their ego, a threat to their sense of self, and that this could be a pathway for people to then engage in violence towards that individual. So let's delve a little deeper into this process of measurement and control. And we're going to start off talking about dependent variables. So remember, dependent variables are the outcomes, the effects that are hopefully observed by our proposed or hypothesized cause. So all true experiments have a dependent variable, and they all include at least what we call a post-test, which is a measurement of the outcome in both groups or all the groups after the experimental group has received the treatment or the independent variable has been manipulated. So remember we talked about the 3 prongs of causation earlier on in part 1, one of which was time precedence. So that's why we call it a post-test. The outcome is measured after the manipulation of the independent variable. You're creating temporal precedence between the cause, the manipulation of the independent variable, and the effect, the measurement of the dependent variable. So it indicates if the dependent variable is sufficiently sensitive of a test measure. You want one that's going to discriminate the effect differences between the groups. And sometimes this is just an example of a poor tool. You're not using the right measurement. There are certain specific problems we run into. The term that we utilize sometimes for one type of problem is what's called a floor or a ceiling effect. So a floor effect is a dependent a dependent variable, a measurement, a post-test, which fails to discriminate between the people in the groups because everyone scores in a low range. So that's an example of a poor measurement tool because it sort of lumps everyone together. Perhaps the test is too hard, for example. And then you have ceiling effects, which fail to discriminate with all high range scores, which is the test is too easy, essentially. So we have to consider the characteristics of our measurement of the dependent variable. In a sense, how are we operationalizing the concept that we think is the proposed effect in this relationship? Many experiments, many true experiments also have pretests, which measure the dependent variable prior to the intervention. So the idea is that not only do you measure the outcome after the person has received the manipulation of the independent variable, but you also measure it before. And this really allows you, again, to look for a stronger argument of cause and effect because you have the data before the manipulation and you have it after. You can sort of look at the changes not just within the groups, but even within an individual. You can try and look for the examples of that. So in a pretest design, a pretest post-test design, I should say, you have that initial pretest measurement and then you have this post-test measurement. In some cases, the pretest and the post-test, the measurement of the dependent variable, the test can be the same, just administered at opposite times, right? The same test can be given as a pretest and as a post-test, but you've got to consider there's the practice effect we discussed in a previous lecture. Some tests are not valid. They are not reliable, I should say. They have this effect where there's a practice effect. Once you've seen this type of whatever this test is, by virtue of having seen it, you're going to score better the second time you see it. So what you sometimes have to do is utilize alternate forms, which avoids practice effects. So you're, in a sense, what you're doing by using alternate forms is you are controlling for a potential confound, right, of that practice effect. So the measurement method that we utilize, the way we measure the dependent variable, the way we arrive at that set of data, has a direct impact on how we can statistically analyze that information, what that data can then be subjected to in terms of statistics. So, for example, we talked about the levels of measurement in a previous chapter. Dependent variables scaled on a ratio level of measurement, remember, which is sort of has a true 0 point, equal intervals between levels. This allows us to make some specific exact mathematical statements. For example, the Stroop test. Right? The Stroop test response time. It is measured on a ratio scale. Presumably there is a 0 point. You could do it, no one could conceivably complete the Stroop test in 0, but it does exist on the scale that we're utilizing to measure. So a response time of 10 seconds for the congruent word list is twice as fast as a response time of 20 seconds, for example, on the incongruent list, right? You can make those sort of comparisons with a ratio level of measurement. You can say that's twice as fast or half as fast as the other. Dependent variables that are scaled on an interval level of measurement, for example, remember that's the difference between attributes, which doesn't have a real significant, it has significant meaning, but there's no mathematical meaning that can be quantified as one being twice as much as the other. So really the way we measure our dependent variables and our outcomes doesn't need to just be done in a reliable and valid fashion, but it also is going to have an impact on what type of statistics we can then apply. So if we have our independent variable and we have our dependent variable, we have them, we have these operational definitions in place, and we have ways of measuring them, excuse me, and looking for that difference between the groups, then now we have to be mindful of any possible confounds and try and control for them. There are various ways in which we can do this. First and foremost, randomization. As I mentioned earlier, by randomizing, for example, the words on the list, presenting them in a random order, that controls for a possible confound, a couple of possible confounds, things like what are called the primacy effect, the recency effect. If I give you a list of words to memorize, you are much more likely to remember the words at the beginning of the list and at the end of the list. I very frequently administer a test I've mentioned in the class before called the RBANS, the Repeatable Battery for the Assessment of Neuropsychiatric Status, which is a big mouthful. But this test is a cognitive test. It's used as a sort of a baseline, as usually the core of a neuropsychological battery you give someone to measure whether or not they have dementia. And within that, there is a word learning list where the person is presented with a list of 10 words 4 times in a row, 4 trials. So I read this list of words, apple, bell, weather, whatever the words are. I read those 10 words to the person. I ask them to repeat back as many of the words as they can remember. And then I read the list again, and I have them repeat back as many as they can remember, and so on and so forth 4 times. What I've always noticed very, very clearly in administering this test is that people tend to remember the words at the beginning of the list, the first, second, maybe third word, and they tend to remember the last, like 8, 9, and 10 on the list. The words in the middle are less frequently remembered by individuals. So this is an example of the primacy and the recency effect. So one way you can control for any possible confounds within your measurement of your dependent variable is to randomize the order of the questions or that are presented, or in a case of like a memorization list, randomize the order of the words. The other way, or another way we can control for confounds, is to introduce a control variable. So have some feature held constant. In the Stroop test, one thing that's held constant is the number of words on the list. And I showed you these examples, but in the actual traditional Stroop test, there are 25 words in both the congruent and incongruent lists. So you keep it consistent, right? You're trying to reduce any confounds within your measurement of your dependent variable. So you keep things consistent in that way. You control for the number of words on the list. And then another and final way to do it is through statistical control. And this is when you believe that there is a confound, present in the area that you're studying, you can measure that confound. If there's an extraneous factor, a third variable that you're interested in, but that's not what you're studying, but you think it might have an impact, well, you measure it, you get that data, and then when you go to conduct your statistical tests of the effect of the manipulation of the independent variable on the dependent variable, you can incorporate statistically measurement of that potential confound, that control variable, and you can pull its influence out of the results. That's a little hard to wrap your head around if you're not a statistics person necessarily, but the idea is that you can measure how much influence it has on the dependent variable, and then you can pull that influence out to get a truer representation of the connection between the independent and dependent variable and look for that causal relationship. So in the Merznick study, there was a potential confound that was identified, which is that blood pressure can affect cognitive performance. And so what they did was they measured blood pressure for all of their participants, which were all older adults, and then they adjusted their cognitive scores based on that collective blood pressure data. You do this through a statistical technique called an analysis of covariance, which essentially allows you, as I said, to eliminate the influence of a specified third variable. So this is a really excellent way to control for the influence of a confound, because you just you pull the variability out of the measurement that's associated with that third variable. So here we are back at validity and reliability again, right? So let's talk a little bit about validity within an experiment, within a true experiment or a randomized experiment. As I mentioned before, internal validity is kind of the key characteristic of a true experiment, because internal validity is about cause and effect. The internal validity of a study in an experiment really speaks to the logic of the design. the extent to which the procedures and the methods and the measurements that you're utilizing are optimally arranged in such a way that they produce the effect of the independent variable manipulation on the dependent variable. It can be what they call evaluated unambiguously, right? There are a lot of factors in terms of our design of the experiment that affect the internal validity. One is the design sensitivity. So, for example, the levels of my independent variable, right? To go back to Merzenich study, the brain plasticity training level, the computerized, control, and then the no contact control. Those levels need to be sufficiently different from one another, sufficiently distinct, so that I can detect the influence of the independent variable on the dependent variable. The experimental conditions, whether or not they produce this desired hypothesized effect is really based on the design sensitivity. The manipulation of the independent variable has to be strong enough to produce the difference if it exists. If I give you like a watered down version of the condition and then I give you the full-blown condition, there might be too much overlap within those two. So there needs to be a strong manipulation. If I want to look, let me just hypothesize an idea. If I wanted to look at the effect of caffeine on people's performance on a memory test, if I have a control group that receives no caffeine, and then I have a low and high experimental group that receive the equivalent of half a cup of coffee and 1 cup of coffee, that's not a sufficient amount distinction between those levels. It's not a strong enough manipulation that it likely produces much of an effect. Most of us can drink 1 cup of coffee and have pretty minimal impact on those types of things. If I'm really interested in this effect, I may need to have more distinction between my levels. So I might have one group that gets no coffee, I might have one group that gets 1 cup, and one group that gets 5 cups, for example, or 4. Some sufficient level or distinction between those levels of the independent variable that's going to manipulate it strong enough to produce the desired effect. This goes to the idea of reliability as well as validity, but you need to have precision in your measurement of the dependent variable. It needs to be able to pick up on that difference if it's there. And then finally, your participant selection needs to be, and how you assign them to groups and levels of the independent variable needs to be unbiased, and the characteristics that are potentially confounding need to be equivalent across groups. You also want to try and minimize any experimental error that you can, right? This is a way bias and error are synonymous in this thinking. Any influence on the dependent variable that is not solely due to this systematic change that we introduce as the experimenters in the independent variable. And we do this in a variety of ways. We can do this by designing a very rigorous experiment. We can do this by training our researchers and our experimenters to do things consistently the same every way with every participant, so they're not randomly introducing noise into the process, right? So threats to internal validity like this can be addressed via strict and rigorous experimental control and then statistical control by pulling out the influence of confound variables. So that's internal validity. Let's talk about external validity. As you remember, external validity is about generalizability of the findings to other populations, other samples. So there are design components that are really essential for a true experiment and that minimize threats to internal validity, but this makes it more difficult to achieve external validity. And let me explain what I mean by that. I just said that one of the things that you can do within an experiment to increase internal validity is to be extremely rigid and rigorous and create, eliminate noise, right? Make things as simple and straightforward and strong in their manipulations as possible, so you get these distinctions between the levels. But that's not necessarily how things work in the real world, right? There's probably distinctly more shades of gray and variability in how we experience that variable, that concept in our daily lives. So if we design a very rigorous controlled study that has high internal validity, we run the risk of damaging our generalizability, our external validity. So this can happen in a variety of ways. We can talk about sample generalizability. So, are we able to apply the findings to a clearly defined larger population? Do we have a representative sample? We talk about cross-population generalizability. So can I go and now look at these findings and how they relate to other types of subgroups, other populations, other settings, other conditions, other outcomes? These are aspects of external validity in any experiment. there's a term called ecological validity, or the real world impact of research. If I design an extremely sterile laboratory setting, which does a great job of detecting the impact of the manipulation of my independent variable on the dependent variable on the outcome, it might not have ecological validity. It may have no real world impact because that's not how life really is. It's an oversimplified version of how we experience these things, and therefore it lacks external validity. So Merznick's brain plasticity study results demonstrated that brain plasticity training improved performance on standardized tests of mental ability. They found a statistically significant difference between people that received the brain plasticity training versus the other two groups, those that did the computer control or those for which they had no contact. However, those statistically significant differences were not really practically significant, and we'll get into this as time goes on in the section where we discuss statistics. But ultimately, what it was is statistically they did find a difference. But when you look at the actual effect size, the real practical impact that it made, it didn't really amount to any significant improvement in everyday functioning of cognition. It was statistically significant, but it was not practically significant. So it works in the lab, but it doesn't have as much an impact in the real world. So this is a visual graphic from your book that kind of helps to think about generalizability and greater external validity. So remember, we talk about external validity as how well we can generalize to other conditions of the independent variable, other types of independent variables, how we can generalize to other settings, to larger populations, to other outcomes, different types of dependent variables. There's all these different ways in which we want to think about the external validity of our study. Another form of validity that's relevant for experiments is replication validity. So, repetition of the experimental methods that led to a reported finding by a researcher unaffiliated with the original result. This is the definition of replication validity as defined by Frank and Sachs 2012. So the idea is that it's not that I go and then I conduct an experiment and then I conduct a very similar experiment myself and again and again and again, perhaps using only Virginia Tech undergraduates maybe. I'm always the person who's the face of the experiment. I'm the one who's, engaging with the participants. For real replication, what we kind of want to see is that other groups that are unaffiliated, other researchers can find similar results to the original. This is really what we mean when we talk about replication. We want direct, systematic, and conceptual replications. So you talk about the 3 R's when you're trying to discuss whether or not a study has good replication validity. Is the finding replicable? All right. So is the effect size so small that it's not likely to be discovered again with any statistical significance? Is the effect robust, right? If it was a small sample size and you still detected it, then that's a robust effect size. And is the experimental task realistic? That's the 3rd R. Does it have real application to the world? Does it have practical significance that's meaningful? There is a interesting project within scientific research, and we'll talk as time goes on about sort of what's called the replication crisis. But ultimately, there was a study, or there was actually more of a review that was done called the Reproducibility Project, which really gave a numerical value, a numerical rating that reflected the extent to which research on any given topic was contextually sensitive. What they really looked at is studies that addressed topics that were more likely to vary over time. They found that if you were trying to examine things that are more likely to vary over time, then you're not as likely to find replication of that study. So if you're looking at something like anxiety related to finances, and you conduct the study during COVID, prior to COVID, that's a factor that makes it difficult to replicate that study because the context has changed. Other things that reduce the replicability of a study are things like cultural differences. Some studies have, they simply just don't find the same results because of cultural differences across, for example, quote unquote, Eastern and Western things. We talked in a previous lecture about the idea of maximizers and satisficers and how there was a moderating effect that was found by culture in essentially Asian versus Western cultures. Location sometimes is a factor that affects the ability of a study to be replicated. There might be a distinction between people who live in rural versus urban or suburban settings, and they perform differently, and therefore you don't see replication when you change the setting. And then populations, things like a racially diverse population versus a predominantly white one. So this can affect the ability of a study to be replicated. So let's, I guess, come back around to really what's considered the essential characteristic or the essential strength of a true experiment, which is, can causality be established, right? Can we make valid claims about cause and effect based upon scientific research like this? So there are certain issues that were raised in the Merzenich study on brain plasticity that really were presented in a way that talked about cause and effect and whether or not it was really valid. First and foremost, what they found were pretest differences. Okay, and this is a problem that even when we do our best to randomly assign groups, sometimes your groups end up looking different from one another. It's just a fact of chance. It can happen. No matter how good a job we do, sometimes we say, okay, we're randomly assigning whatever this extraneous characteristic or variable is about people that's going to influence the outcome. Well, it'll be equally distributed across our groups. Well, in the Merzenich study, it wasn't, because they did a pretest. They knew this. They found that there was a pre-existing difference among the three groups in terms of the pretest memory performance, and so they did a pre-test measurement of the dependent variable, which was cognitive functioning on a certain test, memory test. And what they found was the experimental group had the lowest pretest scores, just by chance. The people that ended up in that experimental group that got the brain plasticity training, they happened to do worse than their two other groups on average on that pretest. Also, there's the issue of small effect size. As I mentioned, there is a statistically significant finding in the Merzenich study, but the strength of the actual outcome is not great. And that's an important distinction between statistical and practical significance we're going to talk about a little bit more as time goes on. But ultimately what they found was that improvement that was seen amongst people who were in the experimental condition who received the brain plasticity training was practically quite small. That the improvement on the memory scores for the experimental group was really statistically significant, but not really practically significant. In the real world scheme of things, these people would not look that different from one another in terms of performance. It's also a single factor design, which sometimes can be a strength, right? It's very simple and straightforward. But when you're talking about human cognition, human brain functioning, simple and straightforward is not usually a good approach. So the critics of the Merzenich research basically said there are multiple influences in memory and in cognition in particular, beyond just whether or not you've engaged in this type of training. And they only examined one. So really in any psychological study, this is a potential criticism that you may face. And this is why we often want to try and identify potential confounds and measure them so we can control for their influence. There are also some chronic mistakes that we, as human beings, tend to make in our thinking about causality. We've talked about biases a lot. It's a theme throughout your textbook and throughout this class. But heuristic biases in different forms predispose us to mistakenly infer causation. We, as human beings, look for causation. We have a tendency to make assumptions about cause and effect when, in fact, they're just not there. We often mistake correlation for causation, and so we're guilty of this in a lot of different ways. And it's just a part of how our brains tend to work, and it's something we have to be mindful of, and we have to understand about our desire to attribute causes to effects. So we ignore this sort of individual versus group level of analysis distinction. There's this problem where we can always point to anecdotes, we can always look at examples and say, well, that must apply for the group, and then vice versa. We can always make assumptions about groups, and then when you're confronted with an individual from that group, we apply that assumption about them as well. And so your book really defines this in two different ways, that direction of error. So any kind of sort of chronic, repeatable problem in our thinking can be referred to as a fallacy. And in this case, we have the ecological and the reductionist fallacy. The ecological fallacy occurs when conclusions about an individual are based only on analysis of group data of an experiment. So if I conduct the Mersenic study and I find that people that are in the experimental condition, the brain plasticity training, do better on average. That is the key phrase. On average, they did better. I would be committing an ecological fallacy if I plucked one individual out of that brain plasticity training group and said they will do better, right? You will see this cause and effect demonstrated in them. It's the central tendency of the data, right? It's the mean, the median, the mode that is really driving the statistical analysis. And there can always be outliers and exceptions to the rule. The opposite of that is the reductionist fallacy. It's also known as reductionism or the individualist fallacy. And this occurs when data about individuals are used to make inferences about group level processes. This is sort of the problem that we run into when we use anecdotal evidence to as an argument for causation or for a relationship between variables. So this is when we start at the level of an example, an anecdote, an individual who showed a strong, for example, in Mersenic, you find an individual who did very poorly on the memory test, pre-test. They received the plasticity training and they did incredibly well. They showed great improvement. You'd be basically committing the reductionist fallacy to look at that individual point of data and assume that it must apply to the whole experimental group, for example. So these are two fallacies, these are two errors, two heuristic biases in our thinking that we need to be mindful of, we need to pay attention to, because they can really cause us a lot of trouble in terms of inferring causality. So what's the lesson to learn? What do we say about causality? How much trust and how much faith can we have in experiments to produce arguments of causality? First and foremost, consider the facts. Look at as much of the data as you can. Look at studies, look at multiple studies for, looking for consistency and replicability and good, external validity for these types of experiments. Acknowledge the potential for error. Of course, recognize that no design, no experiment is conducted perfectly. There's always potential for error. We always bring biases to the table, and to ignore that is to tempt fate. And minimize generalization beyond the data analyzed. Be careful about how broadly you want to cast the net in terms of how it will apply to the whole population. And that's why we need replication. That's why when you see the same robust and reliable results over and over and over, it increases our confidence in that causal relationship. But simply based on one experiment or even a group of experiments, we have to be careful about how far we want to generalize. So I guess to summarize a little bit, let's just say that a true experiment is a well-controlled, powerful research design where the researcher has complete control over this manipulation of the independent variable. The participants are randomly assigned to groups, to try and control for extraneous variables, for individual characteristics that might be influencing the effect on the dependent variable. And complete control allows for systematically varying the independent variable to analyze how it produces changes in the dependent variable, with the hope that it allows us to then make an argument for a causal relationship. Like, that is really a key aspect of all experimental study. Okay, that completes our lectures on this chapter on experimental design.